going on? There we go. Okay. So today we're going to do 2.7. And then Wednesday, we're going to do 2.8. But since this is my last week, I thought Wednesday I'm going to give you an idea, and we'll do like a practice run of what a sub-lesson plan looks like for you all. That way we can troubleshoot and adjust that process if we need to. It's YZC, ZJT for today. And then Thursday is we'll be done with chapter 2 on Wednesday. So Thursday will be the review day. And then when you come back next week, your first day with the sub is actually going to be a test day. And since next week is kind of weird, it's just Monday, Tuesday, Wednesday, right? You have Thursday, Friday off next week. I'm not going to start a new lesson on a Wednesday of a 4-day break. So here's what I'm going to do instead. You will have from Monday to Wednesday to work on the test. It'll open at 7:30 on Monday, and it'll close at 11:59 p.m. on Wednesday. So you should have plenty of time to Google, look at your notes, look at the web, look at the textbook, look at the video lectures for every single problem. Or not, because you'll start at, at 10 o'clock on Wednesday, and then you're like, I only have 2 hours. Why did I do this? This was such a bad idea. No. All right, here's the bell work for today, at least, though. You need to find the vertical and horizontal asymptotes of this function. I'll give you 3 minutes, and then we'll go over it. Okay. Oh, shoot. I have it muted. That's why. I was like, this dog should have barked by now. Okay. Let's go over this. How do I find the vertical asymptotes? Vertical asymptotes. Oh, did we just stare at our paper for 3 minutes? Like, Mr. Lake, what is this problem? It's an enigma to me. Well, let's look at our notes. Okay, go to 2.6 notes. It's the one that you wrote forever and your hand cramped. Remember that one? At the top of that, it says, I think it's subpoint 3, to find vertical asymptotes, do something. First one to find it had the best Halloween costume. We find it?
I mean, I found stuff talking about it.
What's it say?
Well, one of them is, there's two sections that are down in the class. One of them says the graph, because it has a word class, and the zeros of the
The zeros are the denominator.
Don't divide out with the
Perfect. I love that answer. So I need to find the zeros of the denominator. So I'm going to set this denominator equal to 0. All right. That's great. Okay. Now, how do I solve that? 3 steps. Yeah?
subtract the 16.
Subtract 16.
Divide by the negative 2.
By -2.
And then do the 2
Cube root. That's right. What's the cube root of 8? 2. Okay. Now let's talk about that second part. That don't divide out with the numerator. So this can't be a 0 of the numerator. It's actually really easy to test if that's going to occur. Plug it into the numerator. See if you get 0. Right? So is 3 times 2 cubed plus 7 times 2 squared plus 2, is that equal to 0? And I mean, clear, you don't even have to grab a calculator to find it out. It isn't. If you typed it in, you get 54, which is not 0. So that will not be a factor of the numerator, right? It is not a 0 of the numerator. So x equals 2, that vertical line is a vertical asymptote. All right, horizontal asymptote. To find the horizontal asymptote, what do I have to compare? Yeah, the degrees. What's the degree of the top?
3.
What's the degree of the bottom?
3.
If the exponents are the same, oh gosh, somebody can write, not me, somebody can. If the exponents are the same, then what do I have to do? Yeah, divide the coefficients. If the exponents are the same, I'm going to eat DC. Divide the coefficients. So my coefficients are 3 and -2. So y will equal 3 over -2. Ba, 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 ba. Or -1.5. If it was bigger on top, there would be none. If it was bigger on bottom, it would be y equals 0. And if exponents are the same, you divide the coefficients. Bobo, button, each DC. It's a great acronym because it did happen in the 1800s. There was somebody called Bobo Button, and they ate all of DC. That's why when the nation was first created, the capital wasn't Washington, D.C., right? It was, what was the first capital? Was it in Pennsylvania? Or was it New York? It's either in Pennsylvania or it's New York. Ty's going to get it for us.
New York City.
It's New York City. That was the first capital because blah, 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 in 8 DC. It didn't exist. They had to rebuild it. Then they later changed it after it was rebuilt to Washington, D.C. You can ask all your history teachers about that. They will not be upset with Mr. Lake at all. Yeah. They won't send me angry emails and be like, why are you hurting my students' ability? Well, you learned something today. First capital is in New York City. So really, they should be thanking me, right? I should get thank you emails. All right, here's what we're going to do today. Analyze and sketch graphs of rational functions. Again, this is nothing new. It is just taking everything in chapter 2 and putting it all together in one beautiful problem. Sketching graphs of slant asymptotes. That is new, but it's not difficult. And the same way finding horizontal asymptotes aren't difficult. It's a test. There's a new set of rules that you have to remember how the rule works. But actually using the rule again is really easy. Just like remembering what the rule is for horizontal asymptotes can be tough. But then once you remember, if it's bigger on top, then there's none. The actual application of that is easy, right? It's one of those things. And then this again is just using what you do on your own to solve word problems. And everybody loves word problems. Right? Right. Okay. All right. Let's get the notes out of the way. You could probably, all you need is the highlighted parts of this. You don't need the rest unless it is useful to you to do it. If you want to graph a rational function, you should be able to tell me all of these properties, and they should be labeled or visible on your graph. The first thing is just a good math taking tip for any problem. You should simplify your function if possible. The second thing is when you're really going to start doing math, you need to be able to find, label, and explain what the y-intercepts are. To find the y-intercept, you do the same thing you've been doing since Algebra 1. You just plug in 0 to your function. Wherever you see an x, you put a 0 instead. The answer to that is your y-intercept. The next thing that you need to do is find the zeros of the numerator. Those are your possible x-intercepts. Again, you do that kind of like we did for bell work today. You just take it, you set it equal to 0, you solve. You do the same thing to the denominator. That will give you your possible vertical asymptotes. But before, again, you're just finding this. Before you actually graph anything, you need to check your answers for 3 compared to your answers for 4. Any duplicate zeros are holes in the graph. So if you find out that x equals 2 is a 0 of the numerator, and then you find out that x equals 2 is also a 0 of the denominator, then what you have found out is that x equals 2 is really not an x-intercept. It's not a vertical asymptote. It's a hole in the graph. So basically after you've crossed out any duplicates, the remaining numbers in the numerator are your x-intercepts, and the remaining numbers for your denominator are the vertical asymptotes. Step 5, you need to check for any other asymptotes. What that means is horizontal and slant asymptotes. That's what we mean by the other asymptotes. There are 3 types of asymptotes, 2 of which you already know how to do. Vertical, right, we just talked about. Horizontal is you compare the degrees. Slant is the new one, which we'll talk about later in the lesson. Step 6 is really optional. In fact, I don't know. Unless it asks you to evaluate a point, I wouldn't really do it. The idea is that so far we've created all of these points of interest. To find out what's happening between the points of interest, they suggest you pick an x value between those and plug it in, so it gives you another point to plot, so you can see what the behavior is of your graph. But the easier way to do that is just to actually graph it with the calculator. Right? Graph it in your TI-84, graph it in Desmos, and you will see how the points of interest connect anyway. So really, options 6 and 7 here could be summed up with just 2 words: check with a calculator. So check your work with a calculator to see how to connect what the shape is supposed to look like. But again, that information is all eligible. If I give you a function, I would say graph it and label all x-intercepts. Graph it, label all y-intercepts. There should only ever be one. Graph it, what are the holes of the function, right? What are its vertical asymptotes? What's its horizontal asymptote? And what's its slant asymptote? All right, we're good to move on? Okay, cool. Okay. I said it was a guided practice. I think I'll just do this as an example. Okay, so for example, if I want to graph this, the first thing I do is simplify it. It's already simplified, right? There's no like terms I need to combine or anything like that. The second thing I would do is plot the y-intercept. To find the y-intercept, all you do is plug in 0 for x. So f of 0 would be 0 squared minus 9 over 0 squared minus 2 times 0 minus 3. Which is really just negative 9 over negative 3, which is really just positive 3. So I can plot for my graph that it has a y-intercept of positive 3. Okay, to find my x-intercepts. Again, check your notes. How do you find an x-intercept? You set the numerator equal to 0. So I'm going to write x squared minus 9 equals 0. I'm going to encourage you. I know there's a lot of different ways to solve these, but again, what'll help you solve these in the most efficient way is to factor. Because if you factor it, it'll help you find the rest of the information you need. So this is a difference of squares, right? X squared is a perfect squared and 9 is a perfect square. So it would factor into x plus 3 times x minus 3. And of course, you can always check your work. X times x is x squared. X times negative 3 is negative 3x. But 3 times x is positive 3x. So negative 3x plus 3x is 0, which is why there's no x term. And 3 times negative 3 is negative 9. So this means I have two zeros. X equals negative 3 and x equals positive 3. Don't plot those yet. You might be tempted to plot those, but those are your possible x-intercepts. We have to compare this with our vertical asymptotes to see which ones truly are x-intercepts, it's which ones are just holes in the graph. To find my vertical asymptotes, I do the same thing, but I do it with the denominator. X squared minus 2x minus 3 equals 0. That factors into what? What two numbers multiply to be negative 3, but add to be negative 2? Negative 3 and positive 1. That's exactly right. So that gives me x equals 3 and x equals negative 1. Has zeros. Okay, do you see what I see? Are you picking up what I put down? Look what's happening. X equals 3 is a 0 of the numerator and the denominator. So it is really a hole in the graph. X equals 3. To find, okay, now this is new material. All right, so if you've been zoned out, zone back in. New material right now. To find where the hole is, this is what we have to do. We're going to divide out this factor, x minus 3 and x minus 3. Okay, what I have left then in the numerator is x plus 3 over the factor I have left in the denominator is x plus 1. And then I'm going to plug 3 in for this to find where it happens. So 3 plus 3 over 3 plus 1 is 6 over 4, which is 3 over 2. So the hole is at 3, 1.5. That's where the hole is at. All right, last melon, I need the horizontal asymptote. So to find the horizontal asymptote, I compare the degrees. What's the degree of the top? 2. What's the degree of the bottom? 2. If the exponents are the same, you go to New York City. No, DC, divide the coefficients. 1 divided by 1 is 1. Exponents are the same, so divide the coefficients. 1 divided by 1 is 1. All right, with all this beautiful information, I can now graph this. So it's got a y-intercept I already did. It's got an x-intercept of not 3. That's gone. The only x-intercept left is -3. It's got a vertical asymptote of x equals -1. I really should have done that one in red. It's got a horizontal asymptote of y equals 1. All right, here's what you're waiting for. Again, the new thing, it's got a hole at 3, 1.5. So how I graphed it is at 3, 1.5, I'm going to put an open circle. And again, this is a part where you might look at this and like, I don't know how to draw it from these things, Mr. Like, how do these connect to each other? Well, you go to Desmos. Oh, God. Okay, it's hard to see, but right there. You look at it, it looks like, okay, it goes up to the left and then down to the right. No, this isn't the right one. Oh, no. JK on all of that. X squared. I was going to say, that doesn't match at all. Okay, there we go. That's more appropriate. You look as it goes down and to the left here, and then up and to the right here. And this is why, okay, you might be tempted to say, Mr. Like, do I really have to do all that stuff? You do. Because look at this graph. Do you, at 3, do you see a hole? Because at 2.9, it exists. At 2.99, it exists. At 2.999, it exists. At 3.1, at 3.01, 3.001. At every point, as you get closer and closer to exist, there's just an individual pixel that you can't even see that's undefined at 3. And your calculator won't show you that. All right. But anyway, so that I connect it like this, woo, and like this, woo. Wasn't that fun? Yeah. Not too bad. Just use everything you do in chapter 1 and all your algebra 2 skills on how to solve polynomials and quadratics combined with, everything you know about linear problems, graphing linear, horizontal, and vertical equations, just all the math you've ever learned in your life put together in one problem. It's great. All right, I'm going to clear this and move on unless someone says no. Okay. So here's the other task that you need to do. You don't take notes over this. I mean, yeah, if you want to go back and you can take notes on it, but this is in your notes, I think 2 times already. So you already have the parent function of your notes graphed. It's just y equals 1 over x. That's what a rational function looks like traditionally. And any other rational function can be created from this one by transformations, like reflections, translations, all that good stuff. So I don't think we're actually going to do through this. We'll just talk through it. Can anyone tell me what the negative would do, what transformation that is? What do negatives do? Oh, no. It rhymes with deflection. It reflects it, right? It reflects it over the x-axis. If the negative was down here by the x, then it would reflect it over the y-axis. What's the +2 do? Which way does it move it? Since it's by the x, it's going to move it. Okay, hold on. You're both right. It moves it left, right? Because it's by the x, it moves it left or right. And again, because it's positive, it does the opposite of what you would think whenever with the x, so it moves it left. So I could graph this from the parent function by just flipping it over and moving it left. Even if you forgot that, though, you just graph it on the calculator, right? And then you look and see, okay, it flipped it over and it moved it left. Okay. All right, the -1 then would move it to the right. And then the +3 moves it up. So this would move it right 1, up 3. And again, if you didn't remember that, or you're not sure, is it left or right, you graph it and you see, and you'll be fine. Okay, so the last thing that is new that I do want you to put in your notes is I said there's one more asymptote we have to find, and then that adds every property that we need about rational function. And it is slant asymptotes. A rational function will only have a slant asymptote if the degree of the numerator is exactly one more than the degree of the denominator. If it does, then it has a slant asymptote. If it doesn't, then it doesn't. So for example, x cubed over x squared. The degree of the numerator is 3, which is exactly one more than the degree of the denominator, 2. All right, so again, this will be on bell work on Wednesday. When you see the bell work problem, don't sit and suffer for 3 minutes. Look for your notes. To find a slant asymptote, you use division, ignoring the remainder. So to find out what the slant asymptote is, you actually divide them. And that will tell you the answer. For example, let's say f of x was x squared minus x over x plus 1. Does this function have a slant intercept? Yes, because the degree of the numerator is 2, which is exactly one more than the degree of the denominator, 1. To find out what the slant asymptote is, I'm actually going to divide them. And I actually don't have to use long division for this, right? That is eligible to do synthetic division. I could use the shortcut. So if I divide that, I would do -1 and divide. It's 1, -1, 0. All. Is everyone okay with the setup of that? So remember, you do the opposite sign here, and then we write our coefficients. I have 1x squared, -1 x's, and 0 constants. And I run through. Drop down, multiply by -1. Add down, multiply by -1. Add down. And actually, again, I don't care what the remainder is. It has no matter to me at all. What I care about is this. That is the equation of my slant asymptote. The slant asymptote is y equals 1x minus 2. So what that means is this. Oh, I'm going to do it in blue. That line is a linear equation. It has a slope of 1 and goes through the y-intercept at -2. That's this line right here, y equals x minus 2. My rational function will approach that line as you go to infinity. So it'll look like this. Note that this has a vertical asymptote at -1. Right? So the idea here is as I go to positive infinity, my rational function approaches this slant. And as I go to negative infinity, it again approaches that same linear equation. Notice that a function can't have a slant and a horizontal asymptote, right? Because it's bigger on top, so it has no horizontal asymptote. So a function can never have both a slant and a horizontal asymptote. That would be crazy. I don't know. Should we try one more? Anybody need more time to write? All right, then this is what we'll finish off. A collaborative exercise, yay! Our guided practice day. Just you don't need to graph it or anything. Just tell me what the slant asymptote is. While you're working, as a reminder, if you need any more examples, or if what I just said to you makes absolutely no sense, I would encourage you to use your resources, read the textbook, watch the videos at website, ask Mr. Lake, hey, what the heck were you talking about? Or at 3 p.m., go on to calcchat.com and say, hey, my teacher regularly has no idea what's going on. Can you help me out with how to do problem number or whatever? And they would go, sure thing. We get that all the time. And they'd be like, oh, my teacher's Mr. Lake. I'd be like, what? No, that person expertly defines everything, right? How could you? Oh my gosh. Nominated for Teacher of the Year 5 years in a row. Never won, but nominated. Sure, he nominates himself every year, but that's not an accolade you can take away from someone, right? Oh shoot, I was supposed to do more announcements. Oh my gosh, that's okay. We still got time. By the way, so what your classes will look like, just as a heads up for when you have, when I'm on paternity leave next week, is you will have only 2 lessons a week. It's going to go at a slower pace. Wednesdays will be review work days for you. Every once in a while, maybe a quiz or test. -2 y equals x. Or if you want to think y equals 1x plus 0, therefore y equals x. That's the slant asymptote. So you only have 2 homework assignments a week. That way you'll have more time to use your resources or whatever. But basically the sub's going to say, all right, welcome to class. You should have read this last night. If you didn't, read these pages of the textbook. Then watch these videos on website. Then do the homework. If you get stuck, I don't know, he might be able to help you. But if not, you got other math teachers here at T West. You got Calc Chat. You send me an email. Maybe I'll be bored. Trying to get the baby to sleep and answering math emails. Who knows? All right. Have a good one, everybody. I'll see you Wednesday for like a practice run of that process.